Welcome everyone. As Mohsen has introduced me, I am Attia Gul from Medical Physics Department of INOR Abbottabad. Today I'll talk about different detectors used for small field dosimetry. Mainly I'll focus to give a brief review of different commercially available detectors that can be used in small fields. We will look into the starting from conventional detectors and then moving towards specialized detectors and their behavior in small fields, advantages, disadvantages, and their implication of using these detectors in small fields. We will see all these aspects in today's talk. So this is a brief review.
Father, girl, grandma, grandpa, mother.
Excuse me. This is a brief layout of my presentation. First, I'll introduce what are small fields, and then why it is important to use appropriate detector. What could be the implications of using wrong detector in small fields? And then overview of different detectors, starting from conventional detectors, and then some specialized detectors like plastic scintillators, galvanic films, micro ion chambers, and diode detectors. And then I'll present a study on measurement in small fields with different detectors. We will compare different detectors in this study. And finally, a brief summary. So what are the small fields? We know traditional fields that are used in conventional radiotherapy are in the range of 4 by 4 to 40 by 40 centimeter squares. Generally speaking, field sizes smaller than 4 by 4 centimeter square are called small fields. And why these fields are important? Because these are used in all modern techniques of radiotherapy, including IMRT, SBRT, and SRS. Small field dosimetry have some challenges, and these challenges basically define the condition of small fields scientifically. First condition is loss of lateral charge particle equilibrium. As we all know, existence of lateral charge particle equilibrium is the basic condition. It is a general condition for doing dosimetry, and all theorems and all laws like Bragg-Gray cavity theory, these are valid only in the presence of lateral charge particle equilibrium. But in small fields, we lose this condition, and we don't have lateral charge particle equilibrium. This is a general challenge, general condition. There is another condition, that is partial occlusion of primary photon source. And it is machine related situation that may vary from machine to machine. We see in small fields, the radiation source is partially blocked by the collimators, due to which there is an overlapping of penumbra. You know, in any dosimetry, we need to have a uniform fluence, a uniform beam for dosimetry. But this condition is lost in small fields due to overlapping of penumbra. So again, this is a challenge. And then it comes detector related issues. In detector related issues, first is usually volume averaging effect that arises due to the finite size of detector. When size of detector is comparable or larger than the beam, radiation beam, then it will not give a true dose. It will average out the dose over its volume, and it will under respond. That is called volume averaging effect. Similarly, there are some detectors that have high Z material. These are not water equivalent. So again, they cause perturbations, and they need to be corrected for it. So using inappropriate detectors in small fields can cause significant errors, as we can see in this figure. If we use pinpoint detectors, then we can, in radial direction, we can have an error of up to 35% in smallest field size, about 4 mm field size. But if we use the same detector in perpendicular direction, this error can be reduced to 13%. The best detector among these one is the EBT3 films. Their error is less than 1%. And if we see the diodes, then their error is in positive direction because they over respond. Some incidents have also been reported in radiotherapy due to errors in small field dosimetry. One of these is this incident that was occurred in CHU hospital in France, and that was reported in 2007. The main cause was using an inappropriate measuring device for dosimetry. So we need to be careful when we work in small fields. All of you must be knowing about this IAEA APM protocol TRS 398. It basically provides, it is a detailed document on small field dosimetry. The main aspects that it covers is basically it provides formalism for reference dosimetry in non-standard fields. You know, standard field is 10 by 10 centimeter square for our general dosimetry that we perform every month. But there are many machines, modern machines, where we cannot acquire this standard field. We have to look for a machine specific reference field. And the IAEA protocol 3, there is a mistake. I should have written here 483. This TRS 483 protocol, it gives us a concept of machine specific reference field that is as close to 10 by 10 centimeter square field size as possible. For example, for cyber knife, it is 6 centimeter diameter. For tomotherapy, it is 10 by 5 centimeter square. And similarly, for different type of add-on MLCs, different MSRs are given in this protocol that are close to 10 by 10 centimeter square field. But this is not our topic of discussion today. We will mainly deal with relative dosimetry in small fields in today's talks. In addition to this, this protocol also provides us a guideline for detector selection, both for reference dosimetry in non-standard fields as well as relative dosimetry in small fields. And it also gives a review of different small field detectors. Then it also provides correction factors for different detectors that are commercially available. And we can use these correction factors in our clinical setup. Basically, this formalism, this protocol is based on a formalism that was proposed by Alfonso in 2009 for reference dosimetry as well as relative dosimetry. So going a bit into detail of relative dosimetry in small fields, as you all know, relative dosimetry includes measuring percentage depth doses and then beam profiles and then output factors. But for small fields, output factors are termed as field output factors in this code of practice. Output factor or field output factor is simply a ratio of dose in given field to dose in reference field. And if we are using conventional fields, then we can take a ratio of detector reading in given field to the reference field. But for small fields, we have to employ a correction factor in addition to this ratio. And these correction factors, I was talking about these correction factors, that these are provided in TRS 483. If we go into detail of field output factor or field vectors, there are two methods through which we can measure field factors. One is the direct method, in which only one detector is required to measure. I have used the same notations that are used in TRS 483. F clinical denotes a small field. So it is ratio of detector reading in small field to the detector reading in machine specific reference fields, and then multiplied by a correction factor that is provided in TRS 483 for different detectors for different field sizes. There is another method that is called intermediate field method, or also called as daisy chain correction method. In this method, an intermediate field is chosen and two detectors are used. One is the standard ionization chamber, and intermediate field is chosen such that it is not small field. That is, there is no loss of lateral charge particle equilibrium. Its size is appropriate as compared to ion chamber, and then we can use this formula. For that purpose, this correction factor becomes 1, and this correction factor from intermediate to small field, we can determine it from this formula. And again, the values of these correction factor can be acquired from TRS 483. So these are two methods that can be used for small fields output factor measurement or field factor measurement. When we talk about small field, we need to define effective field size. That is defined as square root of full width half maximum in cross line and full width half maximum of inline profile. When we talk about small fields, then this effective field size differs considerably in small fields. As in this study that was published in 2020, we can see that for nominal field size of 0.5 by 0.5, the effective field size was much different when it was made with MLCs, and same is the case with 10 MB, but it is not very considerable for larger or broad fields. So what could be the necessary and desired detector properties, especially for, in general, for all field sizes and especially for small fields? Our detector should have high spatial resolution, high signal to noise ratio. It should not be energy dependent, and should have lowest directional dependence. It should show a dose rate linearity. It should be stable, handy, and easy to use in clinic. And last but not least, it should be inexpensive, especially for low budget departments. There is a criteria for choosing detectors in small fields, especially for field output factor measurement. It has been reported that if correction factor of a detector is less than 2%, it can be used without applying this correction factor because it would not cause a considerable implication. And if its correction factor is in the range of 2 to 5%, it must be used with its correction factor. But if its correction factor is greater than 5%, then such detector should not be used for field factor measurements. So next, I will give a brief overview of different commercially available detectors for small fields. Small field detectors could be active detectors or passive detectors. Passive detectors include alanine or gas chromic films. These are sort of gold standard detectors which do not require any correction or any calibration factors, etc. And active detectors, of course, we all prefer using active detectors because they are easy to use and they give us online readings. And these include our ion chambers, diodes, liquid ion chamber that is no more commercially available, diamond detector, very expensive, and plastic scintillators. So if we go into detail of these detectors, let us start from conventional detectors. All of us must be using farmer chambers for our routine reference dosimetry in our clinics. We know all that its volume is very large, that is up to about 0.6 cc. So using this chamber in small fields is out of question. Uh, it can give an error of up to 60% for field size of 1 by 1 centimeter square. Then we also have, all must be having compact or mini ion chambers that are usually used for our commissioning and routine beam profile and PDD measurements. IBA, it's CC13, and in PTW it is semiflex ion chambers. Its volume is about 0.1 cc. For example, for CC13, its volume is 0.13 cc, and for semiflex PTW, its volume is about 0.145 cc. But it gives us an error of about 15% for field size of 1 by 1 centimeter square. Again, we cannot use it for this field size. There is another detector. Many clinics, many departments must be having it. We also have this detector, linear diode array. Basically, this is used not for small field dosimetry, but it is used for dynamic fields. In past, when we used to measure enhanced dynamic wedge profiles, then we were using this linear diode array. So basically, it is used for dynamic fields and in one dimension. But George et al., they have used this diode array in small fields, and they have showed that it gives less signal fluctuation. Of course, when because this diode array, it measures and it scans all the radiation fields at once, but our ion chambers, they move from point to point for beam scanning of the beam profiles and like that. So these detectors give point detectors, they give signal fluctuation, but this array, it shows less signal fluctuation. Also, it gives significant reduction in measurement time, again because it measures it at once and does not need to move from point to point to measure a complete beam profile. We have also studied this detector in detail and covered some areas that were not reported in George's study. And we have found that this detector is not suitable for field sizes smaller than 2 by 2 centimeters square. It also shows a larger penumbra width because it has wider diode spacing. Although diode is very small in size, but spaces between two diodes in this array is large enough, that is 5 mm. So such a large spacing may give a huge volume averaging effect, especially in small fields. Another factor due to which we should not use it for small fields is its packaging and extracameral component that may cause perturbations. And also, it can be used only for beam profile measurement, and we cannot use it for PDD and output factor measurements. So then there is another detector, well-known detector, gas chromic films, especially EBT3 films. It is considered as a gold standard for small field dosimetry. And in previous slides, my previous slides, I have shown that it gives a very minimal error in small fields. That is why this can be used as gold standards for small field dosimetry. It is a two-dimensional detector and it has a very high spatial resolution. It can be used for beam profiles and field factors, field output factors, but we cannot use these diachromic films for PDD measurement. What are the disadvantages? Of course, we have to use it in solid phantoms. What are the disadvantages of using gas chromic films? It requires very strict handling, irradiation and processing protocol. For example, you have to be very, very careful while handling these detectors. You have to wear gloves. You should take care of timings. Like for every detector, you have to fix the timing. Time, for example, 24 hours. Time you should cut these films at least 24 hours before irradiation. And then during radiation and during handling, you need to be careful. You have to remove all the air spaces between these solid plates of phantom. And after irradiation, you have to wait for a specific time, specific and uniform time for all detectors to scan it. And again, during scanning, you need to be careful. You can place this detector only at a particular place. If you place one detector at one place and the other at other place, their response would be different, and so on. Therefore, it is a very tedious processing. And also, we all like active type of detector, but this is a passive type of detector. That is again its disadvantage. But the why we use it as gold standard, because it gives after all this effort, careful handling, it gives the output factors, field output factors that are most accurate. Another detector for small field dosimetry is plastic scintillators. Its working is based on light production in scintillator, and that light is carried out by optical fiber to the photomultiplier tube that is placed outside the irradiation room, usually at the console area. What are the advantages of using plastic scintillators? It gives us a linear response. It is water equivalent, and it has a high sensitivity. When a detector has high sensitivity, we can make it small. That will that can reduce its volume averaging effect. And another advantage is minimal perturbation factors, because it is water equivalent, and therefore we have minimal perturbation factor. And surprisingly, it is the only detector that has a correction factor of 1. That is, we don't need to apply any correction factor in any small field up to down to 0.3 by 3 or 0.4 when we are using this scintillator detector for field output factor measurement. It has some disadvantages too. For example, we need to correct the signal for Cherenkov light that is produced in the optical fiber, and different methods are proposed for quenching of this Cherenkov light. And also it has low signal to noise ratio. Only commercially available plastic scintillators are Exardin W1 and Exardin W2, sun nuclear. These are sun nuclear detectors. Until 2018, only W1 was available, and it was used only for field factor measurements. But in 2019, W2 was also made commercially available that can also measure beam profiles and PDDs. Therefore, it can provide a complete set of relative dosimetry in small fields. This is the table taken from TRS 398. It is the correction factor. You can see that correction factors for plastic scintillator, W1 plastic scintillator, is 1 for fields as small as 0.4 by 0.4 centimeters square. You can see it here. Then small field ion chambers, as you all know, it is big backbone of our dosimetry. And usually for small fields, we use micro ion chambers. For IBA, it includes CC01, and then its improved version that has same volume but with some improvement, IBA razor chamber, and our PTW pinpoint chambers. Then also there is another IBA razor nano chamber, that is smallest commercially available ion chamber with the active volume of 0.003 cc. Basically, it is spherical in shape. It shows two effects. One is the volume average effect that arises due to finite size of detector, because it is not that sensitive, therefore it has a finite size, and due to this finite size, it exhibits volume averaging effect. Some of the ion chambers may also exhibit perturbation effects due to its wall, due to its central electrode. For example, IBA-CC01 has steel electrode that is highly material, of course, and it gives perturbation. And to correct for the problems that were rising due to IBA-CC01, they improved it to IBA razor chamber that has aluminum electrode. Our ion chamber needs to be corrected for polarity and recombination effect. So to correct for this polarity and recombination effect, we need 3 times extra time for measurement. And one advantage of using this detector is that using ion chamber is that it can be using axial as well as radial orientation. It is cylindrical shape. In radial orientation, it renders larger size to the beam, but in like this is radial orientation, so it renders larger size to the beam, but in axial direction, it renders smaller size to the beam, therefore volume averaging effect is decreased. And also in axial direction, polarity and recombination effect is increased due to cable irradiation and stem effect, etc. But in radial orientation, because it gives high volume averaging effect, that is why it gives an error of up to 25% in 0.5 by 0.5 centimeter square field size. What are the recommended scan directions for ion chambers? We can use ion chamber for scanning if its direction is perpendicular to the scan direction. For example, we can use this ion chamber in axial direction to acquire X profile as well as Y profile, cross line as well as inline profile. Similarly, in radial direction, we can use only this direction where the direction of ion chamber is perpendicular to scan direction, but we cannot use, it is not recommended to use parallel direction because it gives again stem effect and cable irradiation, etc., due to which beam profiles measurement may affect considerably. And there are some limitations for small field ion chambers, that is field size limitation. Because for beam profiling, its smallest field size that can be measured with ion chambers is 2 by 2 centimeter square for most of the micro ion chambers. And for field factor measurement, we can use a small field ion chamber only if its fraction factor is less than 5%, as I have already told in a previous slide, telling about the criteria of choosing detector. You can see that for all the ion chamber, this is the table that is taken from IATRS 483, where different ion chambers are shown. And you can see for all these ion chambers, they have provided fraction factor only for those fields where its fraction factor is less than 5%. And for all these fields, their fraction factors must be more than 5%, and not, we cannot use these ion chambers in these field sizes. IBA CC01 can be used for field down to 0.6, but our PTW semi-flex that is mostly available in many centers, we can measure field output factor only for fields down to 0.1, 0.5 centimeter. Okay, then it comes another type of detector, that is diode detector. It has high spatial resolution, that is why their size, because their size is very small, and actually it has high sensitivity, therefore can be manufactured in small size. But its issue is that it is energy dependent. But energy dependence is not an issue in small fields, but because in small fields there is not much energy difference along the depth of the phantom. Or because in energy, it is also not an issue in small fields, because in small fields scattering component is negligible. This diode detector, these have high Z material, that is why they cause perturbations and they over respond. That is why their response is always, their error is always more than in positive direction. For small fields, unshielded diodes are designed that can reduce perturbations further. Examples of diode detectors could be shielded diode like IBA PFD, and PTW shielded diode like PTW P60016 diode. And there are also some commercially available unshielded diodes like IBA EFD and IBA SFD, IBA laser diode, and PTW. There are some PTW unshielded diodes too. What are the recommended scan direction for diodes? Only one direction. Diode should be in axial direction to beam. We cannot place it in radial direction because this is the active volume of diode and it should be facing the beam like that. Unshielded diodes can be employed for a wider range of field sizes compared to shielded diodes. Again, this table is taken from IEA-TRS 483, where correction factors for different shielded and unshielded diodes are presented. You can see this is an unshielded diode, and its correction factor is provided down to 0.967. That is, we can use this diode for 4 mm field size also, but we cannot use this shielded diode for fields smaller than 0.8. Similarly, PTW 60016 shielded diode. The smallest field size that we can measure field output factor for is 1.2 centimeter, and we cannot use it for smaller field sizes. Therefore, unshielded diodes give better response in small fields. Now I will present a study, my study that on measurement in small fields with different detectors. I have compared different detectors, including atomic films, laser nanochambers, pinpoint ion chamber, stereotactic field diode, and laser diode. I will also present correction factor of these detectors, because their correction factors are not available in TRS 483 that was published in November 2017, but these detectors were made commercially available after that. So this is the field factor measurement with unshielded stereotactic field diode and EPT3 films. We use two methods, direct method and intermediate field method, and we can see that their results agree well with each other for all fields, for 6 MP as well as 10 MP. And then this is the output ratio without using any correction factor. Here we can see that the pinpoint ion chamber, they under respond due to volume averaging effect, and this effect is more pronounced in radial direction as compared to axial direction. The response of all other detectors, including laser nano chamber, their response agree well with each other for all field sizes, for all energies. So this table provides correction factor for different ion chambers, for different detectors, including laser diode, laser nano chamber, PTW pinpoint chamber in radial orientation and in axial orientation. Actually, 31023, its correction factor is not available in TRS 483 because it is the new pinpoint detector with improved geometry. Here, all green column, green entries, these correction factors are less than 2%. Therefore, these detectors can be used in these field sizes without applying any correction factor. But this pink one, their correction factor is more in the range of 2 to 5%, and therefore we should use these correction factors when we use these detectors in these field sizes. But for PTW ion chamber, for smallest field size of 0.5 by 0.5, we see an error of up to 12 or 13%, and therefore we cannot even use these detectors even with correction factor. We cannot use this pinpoint ion chamber in these fields. This is the result of using different detectors for beam profile measurement in smallest field size of 0.5 by 0.5 and standard field of 10 by 10 centimeters square. For 10 by 10, we see their response difference is less than 2%. But for 0.5 by 0.5, for PTW, their response is error is up to 18% for 6 MV. For axial direction, error is less percent, but again is less, but again it is up to 10%. That is not acceptable. For PDD, all detectors that are used in the study, they are equally good their response is less than 2%. Difference in response is less than 2%. Yeah, so for PDD, we can use any detector. So if we see the summary of commonly used detectors that we can use in small fields, starting from gaphchromic films, we cannot acquire PDDs, but beam profiles and field factor measurement can be done with gaphchromic films. Its advantages include high spatial resolution and this is gold standard for small field dosimetry. But disadvantages are that it is passive detector. It has there is a tedious processing, and it has very strict protocol for handling and irradiation. Then micro ion chambers, their limitation is their field size. We cannot usually use it for fields smaller than 2 by 2 centimeters square, with the exception of this razor nano chamber, where we can use it for even smaller fields. And these are energy independent and also angular independent. We can use it in axial as well as radial orientation. But their disadvantage is that they show some volume averaging effect. They need to be corrected for polarity and recombination, and also due to measurement of polarity correction and recombination correction, it requires long measurement time. Then there are some unshielded diodes. Their size is very small, and they can be used for PDD measurement, beam profile measurement, and field factor measurement. Its advantage is that it is time efficient, because we don't need to measure its polarity correction and recombination correction factor. That is why it is it requires very less time for output factor or beam profile or PDD measurement. Also, it gives a single solution, because we can use these detectors for for complete set of relative dosimetry, and it is also real-time detector. Its only disadvantage is that it has low shelf life. This is the only disadvantage. But when we choose diode, we should go for unshielded diode, because unshielded diode gives us we can measure the field output factors for even smaller fields with unshielded diodes as compared to shielded diodes. For example, I know that many of our centers who have recently procured dosimetry equipment, our have provided us shielded diodes, saying that it can be used for small fields. For example, in most of our centers, we have PTW 60016 shielded diode that can be used only for fields down to 1.2 centimeters square, and we cannot use this detector for smaller fields. So this is not a good choice. If any one of you intend to do small field dosimetry and to procure for new dosimetry system for small fields, then he or she should consider procuring unshielded diodes that are inexpensive as compared to plastic scintillators and diamond detectors, and also equally good for small fields. Thank you. Any question?
Yes, we have a few questions in the chat box.
Let me check chat box.
Mr. Kashif is asking that why GAF chromic films produce accurate results when handling insensitive matter.
Yes, gas chromic film. I personally have used gas chromic films. Although it is very difficult to handle and to process and to scan these films, but they give accurate result due to one reason is they have high spatial resolution, very high spatial resolution. That is why their results are comparable to Monte Carlo simulation. That is again considered as gold standard for measurement for dose measurement in small field, dose calculation in small fields.
Thank you. There's another question for your kind attention. What about electron beam from Santanu Purohit?
Sorry, from?
I can't spell the name. It's Santanu Purohit.
Okay. Some studies have also been published for measurements in small fields in electron beam, but because this was not the topic of our today's presentation, that is why I have not much studied about it today. We can discuss it later. So in comparison to laser ion chamber and unshielded diode, what do you recommend? If we see time efficiency, then I'll go for unshielded diode. Unshielded diode is the best detector because it does not require to be corrected for polarity correction and recombination correction. On the other hand, laser ion chamber, not nano chamber, because it yes, although nano chamber it has very low volume averaging effect, but it has very high polarity effect, and it is also, its response is very less stable as compared to other ion chambers. That is why I would personally recommend unshielded diodes based on the its time efficiency, its accuracy, like that.
Assalamu alaikum. I am Asad. Thank you very much, Dr. Attia. I want to ask that for the small field, TRS 483 is a new protocol from the IAEA, if I'm correct. So that is applicable for the LINAC as well, or it is just specific to some specialized machine like CyberKnife, tomotherapy, and gamma knife?
Well, thank you for asking. This TRS 483, it provides, it is applicable for our general purpose Linux also. Not only, rather, I would say very less data is available for CyberKnife and tomotherapy and other gamma knife, etc. Most of the data that it provides, for example, different correction factors, these are all valid for our Linux as well.
So our Linux are commissioned for a nominal field size like up to 3x3, and that's what the recommendation from the variant side. So if we are starting SRS or SBRT, so is there any recommendation for the recommissioning or to make a separate machine for the SRS in the Eclipse or the Monaco system?
Yes, we can use add-on MLCs. We can use SRS cones for that, and of course we need to recommission it for these small fields. But yes, there is a limitation on our Eclipse part. The smallest field size that for which we need to input the field factor data is 2x2 centimeters square. I have personally talked to variant people at different forums, and they say that they will see into the matter.
Are there any more questions?
Yes.
Okay, I guess there are no more questions left. Thank you, Dr. Attia, for a productive session. And I would like to thank all the participants